Yeah, the speaker, Seongsik Kim from Juang University, who would be maybe the candidate of new member.
I'm not.
I don't know. I don't know. Sorry.
His PhD.
Okay, okay. So okay, yeah, sorry. Yeah. Okay. Yeah, he will talk about self-resonant dark matter. Please.
Thank you for introducing and inviting me for this presentation. So I am Seongsik Kim from Juang University and mainly working on a lot of dark matter stuff. So my main work will be I'm mainly working on the dark matter model building or using XMAT, using some theoretical formalism like F matrix and applying them to dark matter physics. So this work is done by my supervisor, Professor Min Lee, and the Binchu, who was the former postdoc in our group, and now he's in the Nantong University. So here is the content. I will talk about at the part one, I will talk about the motivation of our model. Part two, I will talk about the traditional form-operated enhancement, which will be explained later. And part three is our new content, which is the which I will call self-resonant model. And it will be applied for the part four, and it will be analyzed for the dark matter physics. So let's first talk about the motivation. So first, we must define what is dark matter. Is there anybody know what is the dark matter exactly? Just curiosity.
Nobody knows.
Yeah, you do. Yeah, we don't know. There are two things we are quite sure about that. First, their evidence are arise from the gravitational observation, which implies that they interact standard model particles with gravity. If they are dark, I meant they do not interact with photon. They might be purely interacting with photon, but in practical sense, they do not interacting with photons. In usual dark matter model, it is assumed that some hypothetical weak coupling between dark factor and standard model. One of the examples is the WIMP scenario or GIMP scenario or etc. Anyway, such new physics are usually assumed. From the observation, the dark matters are assumed to be non-relativistic.
Right.
Now, it will be explained maybe 2 pages later. And so their existence are prepared by cosmological observation. And due to lack of the condition, I mean only few conditions are required, few conditions are given, but so there are too many candidates within range of up to -12, -10 to 22 electron volts to the 10 polar mass, various mass range. So the first evidence of the dark matter comes from the galactic rotation curve. So we can see there are some matter, and we can estimate their distribution by what we see by the photon signal from there. From the photon signals, we estimate the velocity of each astrophysical stuff should follow like these lines, but the effect line turns out is something like this one, which is significant discrepancy between the observation and the estimation.
The result is about the group of galaxies or just one galaxy?
I think it is. I think it is a little bit more scale. So I think it is hard. I'm not. Although I'm.
So you mean just only for one galaxy? So I mean, to the best of my knowledge, there is some different kinds of evidence about dark matter.
Yeah.
The one is for the group of galaxies, and the other one is just only for one galaxy. So, for example, the Andromeda. Yeah. So the graph is for just only one, for only one galaxy or the group of galaxies.
I don't think so because as you can see, there are many much. So
This is a rotation growth, so it's a galaxy.
galaxy.
In the case of a cluster of galaxies, you have the microwaves. It's a different type of matter.
Sorry. This is you can see the matter is measured from the star, right? So actually, yeah. This rotation coefficient is measured from the
It's a
star.
very basic question, maybe I shouldn't ask this, but to be honest, I'm wondering, so. In principle, there must be a chance that there are some matter, no more matter, that
Yeah.
explains the curve, which is not observed, right?
Yeah.
Is that chance possibility excluded by analysis or measurement, or?
You mean normal matter as the particle within the standard model?
Yeah.
The standard model, the only particle that do not interact with is the
And even if they interact with something, maybe the signal is too small or we cannot observe.
but
I mean,
only
I'm just wondering the possibility, is it possible?
but only I don't think it is possible within the standard model. I mean the only particle that does not interact with standard model is neutrino, and which is although it is well known that neutrino is now have non-zero masses, but they are still very light they are still very light. So their abundance is very small in the cosmology. So of course because of non-zero mass, there are something massive stellar neutrino model or the right-handed neutrino model, which have some, for example, for people, it is quite assumed that very heavy existence of the very heavy neutrino, they also can be dark matter candidates. So let me exclude such light-handed neutrino from the standard model. Yeah. So it's not the
I
effort.
think a few years ago, that together with WIMPs, in English, WIMP means wind. There were also searches for machos. And macho, of course, was the opposite of wind.
Yeah.
And people were searching for very small stars which have not enough weight to ignite a helium burning or brine dwarfs. And so objects which are supposed to be very compact and invisible. And here there are two problems. One is in general, because we know from baryogenesis, not baryogenesis, from deep synthesis, that the abundance of baryons in the universe has to be very small, a few percent at most. Because otherwise the predictions of nucleosynthesis don't match. From the observational point of view, people were looking for microlensing of these macho objects, and there are strong bounds. So the idea is that you wait until one of these macho is passing in front of a star, and you have a lensing effect. And so they are monitoring thousands of stars and waiting for this object to pass in front, and in this way they can pull them out.
So, but still, primordial black holes are still involved in the field, right?
Basically, we still expect either MOND, modified gravity, to explain that, or some object which is interacting or.
So the next reason for the dark matter, and the answer to the question why dark matter is cold or non-relating state is this one, the circle formation. So basically, every baryon, we know that at the universe history after the Big Bang of the 380 kilo years, the CMB cosmic microwave backgrounds were arise. Before that, all of baryons and photons are coupled to each other, so they keep scattering, and after the CMB, their fluctuation is now generated. Now generated, and they grow to generate a star. So like this. No idea,
Just quickly, just briefly.
yeah. Okay.
You still have to, this is introduction.
Yeah. So the problem is that the fluctuation generated after CME, let's consider there is no dark matter, is not enough to explain the current observation, which I meant that the time difference between current universe and CME is not enough to generate enough stars and galaxies and etc. There must be from any other force together the barium, gathering barium to generate the stars, which can be explained by the dark matter, the earlier structure, dark matter structure, which is of course non-relativistic. If dark matter are relativistic, they really stream out and they do not make such gravitational fields. But since they are non-relativistic and they decouple quite earlier time, they reform their own structure, and their own structure became a guideline to generate stars and galaxies and etc. And which is in agreement within the simulation and observation. So yeah.
Yeah, just non-relativistic means actually mass, expected mass should be large. No,
I meant no. I meant they are just flow.
slow.
Yeah.
It means actually massive particle, highly massive particle.
Well,
So highly massive particle interact strong gravitational interaction. So for the dark matter, actually we assume weakly coupled.
yeah.
So how to overcome this difficulty? Conflict.
Wait a minute. I think that weakly coupled means that it is still weak but stronger than the gravity. Yeah, it should be.
Gravity is too weak.
Gravity is too weak. Yeah.
It's just enough that it's weaker than we can have.
And one thing that
Weak means actually weaker than weak interaction. Okay.
actually order of the weak interaction. There is some historical reason. And the one thing that I afraid that is that there are some dark matter model with very light dark matter surface that have order of the electron volts. So heavy dark matter. So that times dark matter is heavy is not sometimes is not just justified. For example, axion is such axion. You see the axion is such candidate. So the next evidence is the black cluster. This is the figure. After the collision of the two black clusters, the red stands for the matter distribution from the photon, and the blue stands for the matter distribution indicates from that refers from the gravitational lensing. So our visible standard model particles are gathered in here, while there are something missing, or the matters that we cannot see are passed through in this region. That implies there must be something another particle space outside from the standard model, which is of course dark matter. And this observation follows that there is self-scattering cross-section between dark matter particles less than the 1 centimeter square per gram. These two observations, the structure formation and the black cluster, are based on the large scale structure of the universe. And both of them prefers the coordinate dark matter. On the other hand, small scale structure is the problem that, yeah, the first problem is the Forecast problem for the small scale of the universe. So if dark matter is truly coordinate, their density profile, the function of R to the R as the distance from the center of the structure and this is the center of the structure, is assumed to be some cost program, something like this one. Or in the simulation, this black line indicates the indicates the proper density structure of the galaxies. The problem is that even if we try to fit the data to this NFW profile, which is cost, it is shown that little difference in the flow in the actual data, which is blue, and the simulation is this one. This indicates that dark matter structure do not want to overdense, wants to be overdense. So to avoid the overdense, there must be, it might be, dark matter might be collisional. I meant that if dark matter are collisional, then overdensity structure should be spread out because thanks to their collision. So we can assume the dark matter as the self-interacting species, then Dutch profile is reduced to the flat profile like this blue curve. So to explain this difference between the Collision reef simulation and actual evidence, actual observation, such that perfection for mass range of therefore 1 to 10 and 1 centimeter per gram is required for them. For the documentary.
Sorry, just to summarize, in the previous plot, you had an upper bound. Here you have a lower bound, right?
Yeah.
So you have two different needs.
Yeah. At least this.
So you,
Very
only one point. Yeah, of course, there is a long debate about whether there is a cusp, a core in the center of gas or not. The point, however, is that we always have to remember that simulations do not include baryons. And also, we have no idea what the black hole at the center of the galaxy is doing. It can accumulate more matter or expel it.
Yeah.
In other words, it's very uncertain that the behavior of the density in the very center is kind of still an open question. However, it's true that people don't like to have a cusp. So one possibility is to have this minimal amount.
I heard that there are some simulation that including baryonic effects, although it is not included in this slide.
They are recent simulation.
Actually, I heard such thing yesterday.
Okay.
Yeah.
But usually it's very challenging to do simulations in the very center, including baryons, because it includes microphysics. It's very difficult to simulate.
Yeah, actually, that's the diversity problem. I mean, so this is the simulation diversity. The diversity program is that the density profile between the collision with observation and actual observation, like collision with simulation and actual observation. So you can see a little bit discrepancy between here. This plot does not include baryonic effects. The why it's called the diversity problem. Why the problem is called the diversity is that if you include baryon, some galaxies are matching without self-interacting dark matter, without assuming dark matter to be self-interacting, but some galaxies do not match at all, even you include the baryonic effects. And there are another motivation for the self-interacting dark matter model. One is the two big spell. That is that collision with dark matter must be gathered together, must be make a dense structure, and such dense structure must make a lot of halo in the galaxies, but which is not observed. So their dense profile must be spread out due to their self-interaction, and there also is mission centralized program or the operation of the ultra-faint group galaxies. I think I take too much. Anyway, it's good. Yeah, that's below. So as I say that self-interacting dark matter spreads out the profile and it solves the problem. It can solve the problems. So these are tension. Large scale structure prefers collisionless, and small scale structure prefers collisional dark matter. But this tension might be relaxed if dark matter cross section has the velocity dependence on the velocity. For example, the first large structure has dark matter has larger velocity on the large structure and small relative velocity for the small scale. So to achieve this behavior, we can consider the impact called homocratic enhancement. So let's talk about what is the homocratic enhancement. The homocratic enhancement is basically low velocity, the enhancement of the cross section for the low velocity spaces. In the classical mechanics, consider there is something gravitational force in here. The fast moving particles go so fast, and they have no time to feel gravity, so their trajectory is almost unchanged. But if particles are slowly moving, they feel more time to feel gravity, and their trajectory significantly change. This might be interpreted as effectively the effective enhancement of the impact parameter. That is classical mechanics point of view. In quantum mechanics, QM, the homocratic enhancement is interpreted as the amplification of the wave function at the scattering center. So in the scattering program, it is usually assumed that incident particle and outgoing particle are asymptotically plane wave. It is basically true, but if the potential between them are long range, then the wave function at the center is significantly distorted from the wave limit, and because it is enhanced, because the enhanced wave function value, which stands for the more probability at the center, which directly corresponds to more probability of scattering. So compared to the plane wave approximation and real scattering, the comparison between the scattering cross-section from the plane wave approximation and real scattering cross-section can be interpreted as the homocratic enhancement, and the ratio is called homocratic factor, as in by this formula. Of course, let's talk about the example. What is the famous example of the long-range potential is, of course, the Coulomb potential, which is given by this one. And by forming the Schrödinger equation with the Coulomb potential in the non-bound state, which is collision, you can find the exact solution for the wave function as this. It's this one, and you can evaluate for the factor from here, which is defined as this value. And you can see that the naive plotting, the f particle velocity is smaller compared to factor. The degree of enhancement of the cross section are growing as particle velocity decrease. The first point of view, in quantum field theory, quantum field theory, to evaluate the cross section, we usually consider the three-level as the phenomenologist. We usually just consider the three-level diagram because it is simple and such loops, higher the correction, something like loops are usually ignored, usually negligibly small. But let's consider the alternative scenario. There are some conditions that can make loops amplitude can be greater than the 3 level. At this case, the cross-section evaluated from the 3 level approximation is significantly changed because the real cross-section is determined by this function, determined by these loop diagrams. This difference also interpreted as the form vector, and I will present that these descriptions are actually equivalent to the QM description. I will show that just because our particle model is written in terms of the relativistic quantum field theory. But it is hard to evaluate the form vector directly from the QFT language, so we must change our formalism to the QM, which gave more intuitive and simpler way to evaluate form vector. So this is the quantitative issue. So this is our strategy. We start from the QFT and change to the formalism to the QM and evaluate the form vector. So let's consider what is the condition for the loop dominates the loop amplitude is greater than the 3 level. It requires the resonance condition. It requires resonance, which in this diagram, if the T channel propagator diverges, then it can be such loop diagram might dominate the greater than the 3 level. The condition for this is that first the particle should be non-relativistic. So the non-relativistic quantum mechanics formalism is now valid, and the light mediators are required. And the energy exchange between the particles should go to 0. So all of these T and M maps go to 0 to assume that the particle spaces between the scattering particle spaces should have same mass. So these are all within satisfying these all of 3 conditions, this equation can be achieved. This inequality can be achieved.
Higher question, I think normally actually negligible or weak, but you mean the greater than the 3 level.
Yeah.
So how to understand intuitively? The loop correction is significantly more than the 3 level contribution.
Yeah.
Yeah. So how to understand? H bar
is it's just the becomes of resonance. Consider T minus M and go to 0. Then this is order of 1 over 0. This is order of the 1 over 0 square, which is greater than 1 over 0. Yeah. Yeah.
Then it means if you take into account the higher order corrections,
Yeah.
then
Infinitely. That's right.
So what happens? Then
Exactly.
You can resum them. You resum an infinite number.
so then it means the final answer is getting worse and worse.
Yeah, worse and worse. But we still can treat it by the vector equation. So let's consider that in fact amplitude is dominated by the infinity level diagram, like this one. So we already know that infinity plus 1 is still infinity, right? So let's just assume that this infinity diagram is almost equivalent to the infinity diagram. Let's just attach one more ladder to here. This equation gives because infinity plus infinity 1 is equivalent, so this diagram should be equivalent to the infinity plus one more length, right?
It means corrections are actually convergent.
Yes.
Yeah.
Anyway, within this approximation, this diagram, the equation for this diagram is interpreted as this one, right? Where the G tilde is tree level amplitude given by here, and the G is the propagator of here, and the lambda is the effect amplitude, which is given by the effect amplitude.
Sorry, gamma tilde would.
That is the single one,
Sorry.
the single vertex.
Is it one or higher? One? One or higher diagram implies.
So gamma includes an
Everything.
infinite number of loops.
Yeah.
Infinite number of.
The dots. Infinite plus one equal to infinite.
That is actually, it means higher loops. It's just one loop.
This is one.
So
You add one more.
Every,
Yeah, you
all
just
diagrams are actually one loop. One loop, one loop, one loop.
no.
No, so I
No.
think each square is one group, right?
this square is one loop.
Yes.
Yeah, and all
yeah.
the squares
All the
are
other ones.
loops.
This also is one loop in this node. Yeah, all of them. So this is infinity loop, and this also is infinity loop.
And physically, this means that the system is close to forming a bounce state.
Well,
So what is exactly, no, I'm just wondering the application to standard, to dark matter, that's it.
as you say, this formalism is developed for defining the bound state, but I applied to this formalism to the scattering
Yeah, so
theory.
this is, in the case of dark matter, you don't have bounce states, you
Yeah.
just consider scattering.
Yeah.
So you have some dynamical conditions that you have to,
Well, anyway.
kinematic conditions.
디스트리뷰션이 그 레저넌스.
Yeah.
레저넌스 is cooperative something. 이거는 어떤?
Well, let me go. It is usually considered as non-perturbative.
Yes, in one more term. That's so, but I'm just wondering, this requires some specific conditions on the external momenta,
Yeah,
right? So this P1, P2, K1, K2,
should be non-relativistic.
yes, but they have to obey some specific conditions in order to have the zero momentum in the.
Actually, no. I mean, in non-relativistic, in the only conditions for the external particles are these two, the incident particle and final particle are equivalent. They're physically
So
equivalent.
the only condition is that the propagators are massless. This is.
Propagators are massless, and the particle phases have same masses. Same masses because so that the energy transfer by mediator goes to zero.
So what about different topologies in these diagrams? Like if you, does it matter about the fact that, so you have like one loop at the end and you kind of, like you're kind of adding on one loop at the end.
Yeah.
But
Actually, there's no difference. Because I don't think there are a difference between the level number of infinity and level number of infinity.
Right. But for example, so within one of these diagrams, I mean, you could have one where like two of the lines in the middle are like swapped.
Yeah, you can do that.
Yeah.
In this case, I'm just assuming for in this case for just the reason I take the end one is just for the simplification of the evaluation.
I see. So you consider like any case where you just added another loop, you still have the same.
So whatever happens once can happen infinite times.
Believe or not, but this is actually already known.
There exists only internal momentum Q.
Yeah.
Actually, so you are considering just the multi loops.
Yeah.
So are there any other internal momentum corresponding to, where are they?
Yeah, that's right.
No, but the point is that you just put everything in the blob.
Hmm.
You consider the momentum transfer in the blob.
initially internal momentum.
So you see that you are block there.
However, because the propagator are I forgot the propagator.
Q and Q prime, Q double prime.
Yeah.
Yeah.
In principle, Cauchy integral should be evaluated, but the integral is dominated by the Q minus M mediator, and when M mediate, let's consider that M mediator is just matrix. So integral is dominated by Q square, right? So the integral is dominated when Q square goes to 0.
So what is the condition? So you just consider approximation.
Yeah.
So let me remind you one more time. What is the approximation to get the answer?
This one.
And so, yeah.
Yeah.
These are conditions to get your answer. Okay.
Yeah. Sorry, this is for anyway. Let's continue from this equation. Okay, this equation seems quite hard to evaluate, but we still want to evaluate to go to the right answer. So to solve this integral equation, we first define the Bethe-Salpeter equation as the two propagator times the exact amplitude as this one. The reason why it is called wave function will be explained later. And we of course take the center of frame coordinate, which already simplifies the calculation. And this propagator, of course there might be the loop correction to the propagator, but for simplification, we only consider the single propagator. By multiplying the two propagator in the both sides, we get such like this equation. And there are a lot of conversion steps, but I will skip a lot of derivations due to level of the time and etc. But I must say that because propagator has some there must be this equation must contain a lot of coupling or something numerator in the propagator. All of that effects are contained in this function. The m square, the dimension m square is just due to, for example, if the scattering model is the dimension 3 interaction, then the interaction terms have some m square. The interaction term has mass, so 2 mass is included in here, and if the equal interaction, the spin normalization gives you m square. And we integrate the Bethe-Salpeter wave function by the momentum, by the energy, and by defining this equation reduced to here, and by evaluating here, this is what we get. Integral form of Schrödinger equation. Yeah, that complex equation now reduced to our very known the Schrödinger equation, but it is the integral form. And by solving them, we can evaluate the full factor.
So what is the form of the? So you have a potential, no, an effective potential. What is the potential?
This potential it can be evaluated by the Fourier transformation, and it is just the Yukawa potential. Many to n.
And so the physics, so can you remind again, so the particular model that you are analyzing, so the particular coupling, so for instance, the coupling of your model and so on, they appear where do they are? Is alpha in the alpha parameter? So what are the parameters of the?
Parameters of the alpha.
Okay, you do that at dimensional ground because you didn't fix any model.
Yeah.
Yeah, it's just as, okay. So everything is hidden in alpha and n.
Yeah.
So depending on the model that you have to fix alpha and n.
Yeah.
Could you give me some exact description for the mu and MED and ME? You have
Mu is just the reduced mass, and the MED is mediated mass.
and
Yeah, exactly. Mu, where is it
There
coming?
is the mass and
So what is mu? So mu, exactly. Mu is
here
here.
is some kind of mass parameter to fix some kinds of for the normalization.
No, I forget to define mu here, which is just effective mass that. Yeah, mu is just different. Sorry.
Cannot be just M1 or M2 or.
In this case, the scattering spaces have. I'm sorry. In this case, we assume the same mass for the scattering spaces, so it's just m.
Over two.
Yeah. Yeah, just is.
Because we have the two, but it's just to reduce mass of the two coming.
Yeah.
A similar question to Dr. Ho. Actually, is there any renormalization program to get the final answer? So,
Renormalization.
so you encounter many loops.
Yeah.
So you have to renormalize divergence. So it's
Actually,
tempting to consider mu as a renormalizing parameter. So likewise, is there any renormalization?
actually, that question. There is no there is no problem, but it is due to the approximation of the integral. I mean, just because this is non-relativistic theory, the integral, the cutoff the integral itself is quite reduced to the almost the low energy limit. So
So you need not.
But that integral of the third line,
Right.
that integral is exactly the divergent double in QFT.
this way.
So why we can't ignore that?
No, it is not divergent. It is just decomposition.
What I mean, if you do that integral.
Yeah.
The Q prime four-dimensional integration measure has scale like Q prime to the 3 or Q prime to the 4, and then in the denominator you only have Q prime to the square.
On the
So
right hand
that
side,
integral should be divergent.
Well, it is
chi cm depends on q prime. So what is the degree of q prime in chi cm?
Oh, yeah, that is.
Yes.
so this integral is decomposed here, and this is this, and this integral is divergent. It's not divergent, but it is just
Eventually finite.
and surprisingly it's integer.
Oh, wait, it seems like the second factor is not evaluated. Yeah.
My feeling is that you hide everything in the psi.
Yeah.
Yeah.
You just assume that psi will normalize.
I see.
Oh,
Yeah, well,
the
otherwise
factor
the
here.
final form could be
Yeah.
divergent or not, it
Yeah.
doesn't matter, it seems like just leave that there.
Because when you do the Fourier transform of that object, you just obtain Yukawa normal exponential minus something divided by the denominator times chi. So psi tilde. So psi tilde is has a big carpet under which you pull the dust.
Yeah.
Thanks.
Yeah, it is quite. Yeah, it's quite complex, but. So let's continue. So within this model, I meant since now everything is fine, you can just add the dark matter and light radiator to the standard model with triple integration, something like this. Then some enhancement can solve every problem, like every problem that are related to the discrepancy of the large scale structure and small scale structure. The problem is that this interaction also enhance the dark matter decay to the light mediator. In this scenario, dark matter decay to light mediator process also is enhanced. So, and such light mediator, even theoretically in the active field theoretical view, there must be some interaction between the light mediator and the standard model lepton. And if light mediator can decay to them, the decayed leptons must generate some photon, and it distorts current CMB bound.
Okay,
Yes.
I have a question because, so, of course, there are many models, for instance, with the kinetic mixing and so on, where indeed this dark photon, for instance, this behavior couples to the standard model particles, and so you run into trouble. Because, so basically, you enhance at the same time the self-interaction of dark matter, but you also interact. You have a lot of dark photons, these dark photons, and you can have signals and so on. However, suppose that you have a model where you do not have kinetic mixing. I mean, this mediator is not, so of course, it's a model that is not observable. In such somehow this particle is not interacting with the standard model particles. But I'm just wondering, is there any constraint also in the case when the dark photon doesn't couple to standard model particles? It's just, in the dark center.
We can, but I'm sorry. I'm a little bit confused because in this case we just call that dark photon as dark matter, not the dark photon. In this
it's a dark. Exactly. It's a contribution to the dark matter if it has a small mass, but if it is completely massless, then of course it's not observable. Probably is not excluded.
In that case, I agree with that argument.
Okay, it's just academic.
So what I want to say is that, but in this model, anyway, the dark photon. But I'm a little bit afraid that because in this model, the light mediator, almost the mass light mediator are required, and such dark photon maybe because they are relativistic, they might modify the cosmological evolution, the evolution of the early universe because of the let's call it the GEFF or etc. So anyway, the conclusion is that we want to avoid such a light mediator, but we still want to formulate enhancement. That's the motivation to our model. Let's see again the condition for this one. The T math T minus mediator is written by this one. As I said, dark matter are estimated to be non-relativistic species, so there are no reason to modify the momentum transfer general limit. And in non-relativistic limit, the energy transfer between this particle and this particle is almost determined by their mass difference. So there is no reason for this equation, and there is no reason for M mediator to be zero for this equation. M mediator now can be non-zero if these equations are satisfied. So we consider the model, the dark matter effect becomes to the mediator. So the heavier species are described by the red line, and the lighter species are described by the red line, and their best relationship is satisfying something like this relation. So in our model, there is no light mediator, and although energy transfer is now non-zero, frankly speaking, I exactly don't know why it is interpreted as non-instantaneous interaction, but
M1 is the mediator mass.
not only mediator but also dark matter.
Yeah, then what is the what M2 means?
Second dark matter.
So
this is the two components dark matter model. Yeah.
I see.
Sorry.
So two particles, one is the black one and one is the red one.
Yeah, black one is light
You
one.
postulate a coupling between M1, and 2. So two black and one red.
So you took up this option to avoid the assumption that mediator mass is
Zero, yeah. So although you can see the
Explain why the propagator, the enhancement, where is the enhancement coming from?
yeah, that will be shown.
Okay.
So let's consider, sorry. The enhancement is come from by satisfying this relationship. I mean, the t go to 0. T minus n go to 0. Yeah, but within this relationship, the propagator can be go to the 1/0. Yes, so sorry. So we again evaluated the same equation. And the procedure performing this equation is still almost same, but there are some little difference that because particle mass are almost now is different. So another variable for the central mass coordinate K is now becoming as this one, but still, yes, and the vortexes are now something like very uniform, and you can see in non-relativistic limit, because energy threshold goes to 0, this also goes to 0, and this term vanishes because 2 minus m is almost equivalent to the m2.
What is the meaning of that? Why you have 2 and 1 minus 2?
That is for the resonance.
The resonant, because you have a resonant wait a moment, but M1 and 2 cannot decay into 2 and 1.
That's why we include. That's why we show the almost equivalent. Yeah, I meant that. As you said, in practice, M2 must have mass very slightly lesser than the 2m and 2m1. Yeah.
So the heavy state is slightly lighter than
2m1.
2m2. In other words, it cannot decay.
Yeah.
But very close.
Yeah, it should be very close. The degree of,
so you have
yeah, that's right. It's quite fine-tuning, but still. So first, anyway, by solving this parameter, and you find that the binary equation is given by this one in the position space. So it is same fracturing equation with effective mass of this one, which because of thanks to the fine-tuning or the condition, so the range of potential is quite long range. And the problem is this one. Because of these arguments in the differential equation, it is hard to solve, and it should be treated as numerically. Still, this equation have some spherical symmetry, so we can use the.
Technically, this is not a Schrödinger equation.
Yes.
Because
This
this
is
is
just-
2 over 1.
Yeah.
Which is a factor of 2 or 1/2. So something like
Almost 2.
almost 2.
So after recasting the equation by using the separation of variable, we obtain this equation. And it turns out that only the C factor, which comes from the Yukawa potential, has absolute mass dependence in this equation. But because of the some fine-tuning of this M2 is almost go to M0, this C will correspond is C almost equivalent to the very slow. This C is high. Yeah, sorry. This term exponential to minus Cx almost go to 0. Almost go to 1. So these effects are highly suppressed, and which meaning that this equation, the binary equation, is almost independent of the absolute mass of the particle. So, which stands that the degree of formalistic enhancement is only depends on the tuning ratio, which is defined in B, the mass ratio between M2 and M1, but not their absolute mass.
not on the absolute masses.
Yeah, almost.
And this, sorry, can you repeat again, what is the condition for this to happen? You are very close to the
No relativistic and this mass ratio.
I'm a bit confused there.
So
You reach that equation. For any value of M2 and M1, and then you take the limit, or this equation is valid only when M2 is about 2 and 1?
only M2 is close to M2, M1.
So basically, this is already built in, let's say, it's hardwired. So if you take M2 equal to M1, for instance, this equation doesn't make sense.
Yeah. And then
Only if you have the enhancement. So I'm just wondering if you can recover, no, you cannot. So this equation is obtained by assuming that M2 over M1 is very close to 2
yeah, very close to 2
at the very beginning.
and at the very beginning, yes.
Automatically, this coefficient minus Cx is very small.
Yeah.
This is it. The mass of the mediator, there is an effective mass of the mediator that has to be small.
Yeah, it goes to 0, so it is long range potential. If we can regard this from a potential.
So in other words, if you take this mass, take this capital N,
Yeah.
you take it 0, it works. Then you increase, at some point, this approximation breaks down. But this is only numerically you can see, right? Numerically, it's only numerically you can see.
Actually, C almost 0.
Yeah.
And what is the reason? You ignore the data, the green.
Well, basically because if CF corresponds to MR and M if capital M goes to 0 and by
Are you considering asymptotic region? X goes to infinity?
no,
Capital M is small, right?
but capital M is small. And by taking this by ignoring this term, this equation is now totally irrelevant to the effort mass of the particles. So
It's just enough that M2 is twice M1. But it doesn't matter if M1 is 1 GV and 2 is 2 GV, or M1 is 1 TeV and 2 is 2 TeV.
Yeah.
This is the idea.
yeah, that's the idea for this equation and and they can.
You know what the data can be ignored.
Because they have an effective long-range interaction. Is as if they were a long-range interaction.
Long range means that you are considering just asymptotic region, X, large X.
Yeah, in principle, you are right. There is no reason to this to be ignored by
So but your C is proportional to capital M, right?
capital MR. After this, she as well literally equivalent to the
And
capital
then you
MR.
already chose capital M to be very small by
Yeah.
using M to be small,
Yeah.
close to M1. So C is small.
Yeah.
It's just from the beginning, it's just.
Yeah, that's
Right?
what, if the C is not small, this equation is not valid. So my understanding, is this correct? The equation is not valid.
Of course, as the info, there is no reason to ignore this term. However, if we can ignore this term, this total equation and the solution and form pretty enhancement is totally irrelevant to the effort mass of the document.
Of course, if you ignore.
Yeah, of course.
Yeah.
But you can always do that numerically, no?
Yeah.
So a differential equation, a second order, so
Yeah.
you solve this numerically.
Yeah.
Why did you simulate including that term?
So did you do a numerical calculation in
Yeah.
the
Yeah. No, I did not include it. I think so.
Why did you try to include that term in numerical simulation? So fortunately, you can get the lesson.
Wait a moment, point is Fuchsian, right? Yes, you can solve it. You can have a power function.
So if there is no this argument in here,
Very cool.
prevents to use the power extension for the differentiation.
log 2 is almost 0. No,
No, this is natural log.
I know. 2.7 is
Yeah, 2.7. So it is almost 1.
1.
Close to 1.
Close to one, so
Yeah. So yeah.
1.
So let's evaluate the alpha for each model. We find that these three models are valid for the evaluation. And then for scalar model, we interaction this term, this gives alpha as this value, and the other model gives alpha to be this value.
Okay, so depending on the model, now you change out.
Yeah.
That's it.
For model does not show some enhancement because they show momentum dependency. Yeah.
Which model does not have it? So can
For
you?
example, scalar parameter, just scalar parameter. In that case, it turns out there is some momentum dependent factor.
What is the pseudoscalar and what is the fermion? The
Oh, sorry.
Simon.
Lighter one is fermion, and the heavier one is scalar.
Yeah, of course, it's a problem of parity. Probably. That's why I need a pseudoscalar. Yeah, so the two particles that are approaching are fermions. The two particles. So what is the fermion? Is the dark matter? Which is the dark matter? One of them. So, but one is double of two. So you in the universe you have two species.
Yeah.
One with double the mass of the other.
Yeah.
Because the heavy one cannot decay in the light one, and they are both stable. You don't have relative decay of the time. So maybe it's very stable.
Yeah, that's the as you say, the weakness of our model. Which is naturally here, but okay. So this is the numerically evaluated the homomorphic vector. And you can see that by fine tuning the left ratio, the deepest left ratio, which left gap they define as this one. You can show that deeper homomorphic enhancement for the deeper velocity. So now the small scale gets more enhancement than the regular cluster, velocity of the breadth cluster region. Yeah. So
In our galaxy, the value, what is the value for the? Well, 10 to minus 3, 10 to minus 3. So in general, you can have.
I think here in our galaxy here and the structure that you're in the galaxy for here. So
If you show this picture, in the introduction you said that you need a small cross section for the Bola cluster,
yeah,
and a large cross section and small scale. Depending, so you really need to have delta very small because otherwise they are the same.
yeah, but
So you need
although if the best range is comes to here, then it might be fine, but quite small is required.
And wait a moment, and what happens in the early universe? The universe, the temperature is
Very high. Yeah, it shouldn't be very high, but
the speed is between 10 to minus 1. Okay, so you neglect it. In the universe.
so due to that, the time, let's go faster for the final part, part 4 application and analysis for the documented physics. Our time is 1 hour.
Yeah.
It was supposed to 1 hour presentation, right? Okay. Well, I don't know what here.
That's two.
Yeah. Anyway, our checklist is as follows. Of course, we need to our of course, we need to consider our original motivation, the for the efficiency that's like raw velocity, and we of course need to check the rate density. And there must be other constraints. We consider the indirect detection bound from the CMB. We first need to set a portal that connects to dark sector and standard mode sector. In this case, we assume the dark photon setup, which is given by this one, and view scenario, and for simplicity scalar dark matter model. And to see just the tendency, we just take something like this one, the case of the case, we take some cases with different range of the dark matter and different coupling between dark sector itself and the dark sector and the standard model.
So can you repeat what is X and X? I missed this one.
Sorry, X is the dark photon to the standard model
No.
with interaction like this one.
But this X is not massless.
Yeah. These are massive.
It's massive.
Massive. Yeah. Because we don't want to
Yeah.
So we did some schematic the range density. This is schematic range density. If coupling between the dark sector are strong and coupling between dark sector and standard model sector are weak, then the Walk 2 of particle behaves as dark matter and their range density, their Length density energy and Length energy is almost equivalent, although their number is different, in fact, with the factor of 2. In the contrast, if dark photon coupling is much more stronger than the dark matter coupling between them, only heavier species play a significant role of the current dark matter range density. And we of course need to consider the co-scattering limit. So these three lines stand for the observation. This green line are the
Which observations?
clusters. So this is the large scale. These two are the small scale. These red and blue lines are small scale. So the cross-section data must pass through the both blue and red and green lines. So this is the vertical line is cross-section times velocity for mass equating mass, and this line, the horizontal line stands for the velocity. And by taking this model, we can show that all of the line can pass through the data, which is consistent to the observation.
But this plot doesn't seem. In this plot, the cross sections at larger, for instance, in the bottom cluster, doesn't seem to be so large, so different from that.
Because
it's rescaled. Okay.
Yeah, it's rescaled. So actually the cross section for
So you're just that's why. Sorry. Okay.
Sorry, I'm too fast.
Yeah. Okay. So you are just tilted the plot.
Tilted the plot,
Tilted
yeah.
the plot.
So indirect detection boundaries come from this decay. So because we assume that the particle 1 is the lighter dark matter is connected to the dark photon, and dark photon might be decayed to the standard model, and such decay to the standard model must affect must emit the photon which represents to the CMB fluctuation, which is significantly bound. So such enhancement is characterized by the efficiency factor. So you can see the detailed description of the efficiency factor is difficult, can be found from this paper, but you can see that. And it is simply that the electron position pair produced from dark matter with each energy affects degree of this affects this degree of to the CMB. And for simplicity, we define the average efficiency as such like this one. And from the Planck measurement, we get bound like this value. So this is summary for both benchmark models. So each for each benchmark model, the maximal formal factor is bounded by CMB. The maximum formal as CMB is given like this one. It corresponds to the mass ratio. Each factor corresponds to mass ratio of this one, and corresponding scattering contraction is given by here, and it is possible. So here's the conclusion. And due to lack of time, let me stop here. Thank you.